Hello everyone, my name is Hong Jie and I will be presenting poster number 140 in Qcrypt 2022, titled Large Block Size Toeplitz Hashing Implementation on FPGA. First, allow me to provide an introduction to our project. Randomness extraction is a vital step in quantum key distribution and quantum random number generation. We use a function which is also known as an extractor that has a weakly random source as an input and a uniform seed as the other input. The output of the function are random bits that are epsilon close to the ideal uniform distribution. We chose Toeplitz hashing as our randomness extraction function because Toeplitz hashing is shown to be optimal in terms of output size. Additionally, the straightforward construction and implementation of Toeplitz hashing is another benefit. For implementation platform, we have few programmable gate arrays, FPGAs, versus traditional central processing units, CPUs. For FPGAs, the input power is low, while CPUs draw high power. The size of an FPGA is small too, compared to a desktop CPU. FPGAs execute algorithms in a deeply parallel and pipelined manner, while CPUs are inherently sequential. We may use graphic processing units, GPUs, to execute algorithms in parallel on CPUs, but that will further increase the power and the size of the CPU. Lastly, chip-based integration is much more likely for FPGA implementation compared to CPUs. Thus, the chosen platform for our study is FPGA. In all experiments, we only have access to finite resources. Thus, finite key security is crucial to ensure that we get a meaningful bound on epsilon. This puts forward the requirement of large input sizes to take into account statistical fluctuation. The schematic of our implementation is shown below. We implement the hashing on a Xilinx ZCU111 evaluation board. Firstly, the raw and seed data stored on PC is sent to the processing subsystem on FPGA via 1G Ethernet. The raw data is then transferred from PS to DDR4 RAM memory via the AXI DMA. The Toeplitz hashing call begins operation after the raw data is transferred to DDR4 RAM, which we will discuss in detail next. Finally, the output of the Toeplitz hashing call is sent to processing subsystem via the AXI DMA, and then further sent to the PC via 1G Ethernet for storing and testing. Now, in the Toeplitz hashing call, we first construct the Toeplitz matrix. This matrix has n columns, which are equal to the input size, and m rows, which are equal to the output size. It is a diagonal constant matrix, meaning we only need to fill in the first row and the first column of the matrix with our uniform seed. The entire extraction process is simply a matrix vector multiplication. Now, every computational cycle, one bit of seed data is sent from the processing subsystem to the Toeplitz hashing call, while one bit of raw data is sent from the DDR4 RAM to the same Toeplitz hashing call. The seed bits are accumulated and multiplied with the incoming raw data. At the end of the computational cycle, a shift register is used to shift all the seed bits by one position. And now, the string will be ready to receive the new seed bit in the next computational clock cycle. The Toeplitz hashing call also splits the large Toeplitz matrix into smaller subblock sizes of m prime by n prime. The number of clock cycles our algorithm takes can be estimated using this equation. Notice that the speed up from pipelining depends only on the value of m prime. Over here, we have tabulated the FPGA's resource utilization for varying block sizes. The number of available resources for each column is included in the final row. The resource utilization of our design only increases slightly, even though n increases by 2 orders of magnitude. This shows that our implementation is input size adaptive. Also, we note that the resource utilization is low enough to fit on a small FPGA. In conclusion, we have designed, implemented, and verified a method to perform large block Toeplitz hashing on FPGA. Our method is robust, utilizing a similar amount of resources regardless of the hashing block size. In fact, we were able to perform Toeplitz hashing on FPGA with a block size of 1E9. With this, we aim to bridge the gap in current implementations satisfying the finite size effect. With that, I've come to the end of my poster. Thank you for your time. You can contact me here if you have any questions, and I will be very happy to answer them. Thank you.